Our universe has a hidden birthmark. The story of its beginning is not one of gentle cooling and quiet growth. Instead, the cosmos was forged in a series of violent, sudden transformations, like water shattering into ice in an instant. These are cosmological phase transitions, moments when the very fabric of reality changed state. If such catastrophic shifts really happened, they may have left permanent scars on the universe, ancient wounds frozen into the structure of space itself. By the end of this journey, you will understand how scientists are hunting for these cosmic scars, and what finding them would reveal about the very first moments of everything. We will explore how the entire cosmos might be built upon a hidden lattice of defects, and why the oldest light we see could be hiding the fingerprints of a violent infancy. What would it mean to discover that our universe is fundamentally marked by its own dramatic birth? To find those scars, we must journey back to the very beginning, to a state of being so alien it defies simple description. In the first fleeting fractions of a second, our universe was not a collection of stars and galaxies. It was a seething, unimaginably hot and dense primordial soup. All the energy that would ever become every planet, every person, every distant star was compressed into a volume smaller than a single atom. In that inferno, the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces, were not separate. They were unified into a single master force. Particles as we understand them did not exist. Instead, there was a symmetric, high-energy blur of quantum fields in a state of perfect, featureless chaos. This was a cosmos without structure, without differentiation, where the laws of physics were in their simplest, most symmetric form. But this state of perfect symmetry was inherently unstable. It could not last. As the newborn universe expanded at a fantastic rate, it inevitably cooled. Think of steam billowing from a kettle. As it spreads into the cooler kitchen air, it condenses into visible mist. The cosmos underwent a similar but far more profound condensation. It crossed critical temperature thresholds, moments where the symmetric, high-energy state was no longer sustainable. The universe, in a sense, faced a series of cosmic choices. At each critical juncture, it was forced to settle into a new, lower-energy state, a state with more structure but less symmetry. The properties of our reality were not handed down as fixed constants. They emerged, they evolved through these dramatic, destabilizing events. The stage was being set for the universe to break its own symmetry, and in doing so, potentially fracture its own fabric. This process is known as a cosmological phase transition. We are familiar with phase transitions in daily life. Water turns to steam when it boils, and liquid water becomes solid ice when it freezes. In each case, the substance remains water, but its fundamental state, its properties, and the arrangement of its molecules changes dramatically because of a shift in energy. The early universe underwent similar transformations, but with a staggering difference. It was not a substance within space that changed. It was the vacuum of space itself, the underlying fabric of reality, that shifted from one state to another. The entire cosmos was the substance, cooling and settling into new forms. The driving force behind these cosmic changes is a principle called symmetry breaking. Imagine a perfectly round, smooth ball balanced on the very peak of a steep hill. This ball represents the early universe in a high-energy, symmetric state. Every direction looks the same from that peak. The situation is perfectly balanced but also perfectly unstable. The slightest nudge will send it tumbling down. As the universe expanded and cooled, it was as if that ball was nudged. It could no longer remain in that precarious, symmetric state. It had to roll down into the valley below, settling into a stable, lower-energy configuration. But here is the critical part. That valley is not a single point. The hill might be surrounded by a circular trough. The ball could roll north, south, east, or west. Each direction is equally valid, but each leads to a different final resting place. By choosing one, the perfect symmetry of the peak is broken. The outcome is stable, but it is no longer symmetric. We have actually witnessed a version of this in our own time. The Higgs field, which gives particles their mass, is thought to have undergone this exact process. In the extreme heat of the early universe, the Higgs field had a value of 0 everywhere. It was in that symmetric state, but as the cosmos cooled below a critical temperature, it became energetically favorable for the field to settle into a non-zero value. It chose a direction, so to speak. This breaking of symmetry is what allowed particles like the W and Z bosons to acquire mass, fundamentally shaping the universe that followed. This tells us something profound. The properties we take for granted, like mass and the separation of forces, are not eternal truths. They are the frozen-in results of ancient phase transitions, moments when the vacuum of space chose a new identity. If the Higgs field could undergo such a transition, it is almost certain that other, even more fundamental fields experienced their own dramatic shifts in the universe's first moments. Each one of those events was a potential sculptor of reality, and each one could have left behind its own distinctive scar. To truly grasp how these universe-altering events could leave scars, we need a powerful mental image. Think of the state of the universe not as a single point, but as a landscape of possibilities, a terrain of energy. Physicists call this the scalar field potential, and its most famous shape for a symmetry-breaking transition is whimsically known as the Mexican hat potential. Picture an upturned sombrero, or perhaps the rounded bottom of a wine bottle. At the very center of the brim, there is a small, raised hump. This central peak represents the high-energy, symmetric state of the early universe. It is a precarious place. A marble placed perfectly at that summit is in a state of unstable equilibrium. It possesses a lot of potential energy, and the slightest perturbation will send it rolling away. This is the universe before the phase transition, holding its breath in a fragile, uniform state. As the cosmos cools, the entire energy landscape morphs. That central peak becomes even more unstable, while a circular valley forms around the base of the hat's crown. The marble can no longer stay put. It must roll down from the high-energy peak into the low-energy valley. This is the phase transition itself, the universe shedding excess energy and settling into a new, stable configuration. But here is where the cosmic drama begins. That valley is not a single point, it is a continuous ring. When the marble rolls, it must choose a direction. It could go north, south, east, or any angle in between. Each point on that circular trough is an equally valid, stable resting place. However, once the marble settles into one spot, the perfect symmetry of the peak is irrevocably broken. The universe has made a choice. Now expand this single marble to the scale of the entire cosmos. We are not dealing with one marble, but with an infinite number of them, each representing a region of space. As the universe cools, this transition does not happen everywhere at the exact same instant or in perfect coordination. In one region, the field, our metaphorical marble, might roll and settle pointing north. In a region far away, outside the reach of any signal traveling at the speed of light, it might independently settle pointing east. These regions become cosmic domains, vast volumes of space where the new, broken symmetry state has aligned in a specific direction. The universe becomes a patchwork quilt of domains. This sets the stage for inevitable conflict. What happens at the boundary where a north-pointing domain meets an east-pointing domain? The field cannot smoothly reconcile the two different choices. It cannot be pointing north and east at the same place. Something must give. At these domain walls, the field gets twisted, trapped, or forced into a high-energy configuration. It is along these fiery frontiers, these cosmic seams in the fabric of reality, that permanent scars can form. These are not mere wrinkles, but stable, persistent structures known as topological defects, the fossils of the universe's tumultuous infancy. These twisted boundaries between domains are the scars we are searching for, known to physicists as topological defects. The term sounds abstract, but it describes something remarkably persistent. A topological defect is not a rip in spacetime, but a stable knot, a frozen-in configuration of the cosmic fields that cannot smooth itself out. It is a relic of the old, symmetric order, trapped forever within the new one. Think of it like a wrinkle in a carpet. You can push the wrinkle around, but to fully remove it, you need to lift and relay the entire carpet, an impossible task on the scale of the universe. Once formed, these defects become permanent features of the cosmic landscape, fossils from a fraction of a second after the beginning. Their stability comes from topology, the mathematical study of shapes and properties that remain unchanged even when an object is stretched or bent. Just as a coffee mug and a donut are topologically the same because each has one hole, a defect in a field has a property that cannot be undone by any continuous transformation. It is stuck. The universe expanded and evolved, but these defects simply stretched along with it, thinning out but never vanishing. They are the ultimate survivors from the era of creation. Based purely on geometry and the nature of the broken symmetry, cosmologists can predict what form these scars might take. They fall into three main classes, categorized by their dimensionality. There are two-dimensional sheets called domain walls, one-dimensional lines known as cosmic strings, and zero-dimensional points termed magnetic monopoles. Each type is a potential ghost from a different kind of phase transition, and each would leave a unique and terrifying imprint on the cosmos we see today. Finding any one of them would be like discovering the bones of a mythical creature, proving that our universe's childhood was far more dramatic than we ever dreamed. The simplest of these cosmic scars is a domain wall. Picture the universe divided into colossal neighboring territories, each spanning millions of light years. In one territory, the cosmic field settled into its new state pointing, metaphorically, north. Right next door, it settled pointing south. The boundary between these two domains is a domain wall. It is not a physical barrier you could touch, but a sheer cliff face in the energy landscape, a two-dimensional sheet of concentrated energy slicing through the cosmos. The wall itself is unimaginably thin, perhaps just a fraction of the size of a proton, but it holds a staggering density. A single square patch of domain wall the size of a postage stamp could outweigh Mount Everest. Their gravitational influence would be profound, warping the space around them, bending light, and violently disrupting the distribution of matter, and that presents a universe-ending problem. If even a modest network of these walls formed in the early universe, their collective mass would be so immense that they would have long ago gravitationally dominated everything. They would have crumpled galaxies, twisted the cosmic microwave background into unrecognizable patterns, and essentially overclosed the cosmos, causing it to collapse back on itself in a fraction of its current age. The fact that our universe is old, expanding, and filled with beautifully structured galaxies tells us one thing with great certainty: a pervasive network of domain walls does not exist. Their absence is not a disappointment, it is a crucial clue. It tells physicists that the earliest phase transitions of the universe likely did not break symmetry in a way that allowed these particular scars to form. It rules out entire classes of theories and guides us toward models where the universe chose its new state in a more coordinated, or at least less catastrophically prolific, way. So while we may not be hunting for the walls themselves, we are using their profound absence to map out what could and could not have happened in those first moments. But if domain walls are too catastrophic to exist, another type of scar walks a finer line between possibility and detection. These are cosmic strings, filaments of pure energy so slender they are essentially one-dimensional lines carving through the three-dimensional volume of space. Think of them as the cracks that form when the universe cooled unevenly, like the fissures that race through ice as it freezes. Their scale is almost impossible to grasp. A cosmic string could be thinner than a single proton, yet a single mile of its length might contain more mass than an entire mountain range on Earth. They would be under immense tension, causing them to whip through the cosmos at a significant fraction of light speed, often snapping and connecting into vast, vibrating loops and infinite, sweeping networks. Unlike the problematic domain walls, a sparse network of these strings could, in theory, persist to the present day without destroying the universe's large-scale structure. This makes them a prime target for cosmologists. Their incredible density means they warp spacetime around them with ferocious intensity. A string passing between us and a distant galaxy would act as a razor-sharp gravitational lens, but with a bizarre signature. Instead of smearing or distorting the galaxy's image, the string's unique geometry could slice it, creating two identical mirror image copies of the same galaxy side by side in the sky, a ghostly cosmic double exposure. Astronomers have searched for these telltale pairs in deep field surveys, a painstaking process of scanning the heavens for this very specific, very strange footprint. Their influence may also be written into the oldest light we can see. As these strings vibrate and decay, they would have stirred the primordial plasma of the early universe. This agitation could have left subtle, step-like discontinuities in the temperature of the cosmic microwave background, sudden jumps from a slightly hotter patch to a slightly cooler one along a perfectly straight line. Furthermore, their relentless motion would have generated ripples in space-time gravitational waves, contributing to a faint, persistent hum that we might now be on the verge of hearing. The hunt for cosmic strings is a search for the cracks in reality itself, the lingering scars from a moment when the universe chose its fundamental shape, and in doing so, may have left behind threads of pure energy woven into the fabric of everything. While strings are lines of energy, the most concentrated scars of all would be mere points. These are magnetic monopoles, hypothetical particles that are pure, isolated magnetic charges. Every magnet you have ever held has both a north and a south pole inextricably linked together. Snap a bar magnet in half, and you do not get isolated poles. You get two new, smaller magnets, each with its own north and south. A magnetic monopole, however, would be a fundamental particle that is only north or only south, a solitary, wandering point of pure magnetic charge. Their existence is predicted by nearly every grand unified theory, which attempts to describe how the strong nuclear force and the electroweak force were once a single, symmetrical entity. When that primordial symmetry broke in a phase transition, the mathematics suggest that stable, point-like defects monopoles should have condensed out of the energy field in staggering numbers. The production would have been so prolific that these incredibly heavy, stable particles should be as common today as protons, saturating the cosmos and dominating its mass. This creates a glaring contradiction known as the monopole problem. We do not see them, not in particle accelerators, not in cosmic rays, not in the composition of matter anywhere. Their profound absence is a silent scream in our cosmological data, a clue that our simple picture of a cooling, transitioning universe is missing a crucial chapter. The need to explain this overwhelming absence was one of the primary motivations for the theory of cosmic inflation. The idea is that a fleeting period of hyper-accelerated expansion, occurring just after the grand unification transition, would have stretched space itself so dramatically that it would have diluted any pre-existing monopoles to a density of virtually zero in our observable patch of the universe. In this way, the search for a scar that isn't there, the missing monopole, led directly to one of the most transformative ideas in modern cosmology, suggesting that the universe's infancy was even more dramatic and explosive than we first imagined. But not all phase transitions are created equal, and the violence of the event determines what kind of scar, if any, is left behind. The universe had two primary ways to shift its state, and the difference between them is the difference between a smooth fade and a shattering explosion. The first type is known as a second-order or continuous transition. Think of a simple iron magnet. When it is hot, its internal atoms are jumbled and chaotic, and it holds no overall magnetic field. As it cools past a specific temperature, the atoms gradually align themselves and a magnetic field smoothly emerges. There is no sudden jump, no dramatic release of energy. The change is continuous. In the cosmic context, such a transition could still produce topological scars like cosmic strings, as different domains of the new phase form and lock into place. But the process itself is relatively calm and orderly. A first-order phase transition is an entirely different beast. It is discontinuous and explosively violent. The classic example is water boiling. Liquid water exists comfortably until it reaches 100 degrees Celsius. At that point, it does not simply and smoothly become vapor. Instead, it undergoes a jarring, discontinuous leap. Bubbles of steam violently erupt within the liquid, expanding rapidly as the system releases a huge amount of latent heat. The old phase and the new phase coexist in a turbulent battle until the transformation is complete. In the early universe, a first-order transition would not be a gentle realignment. It would be a catastrophic event where the fabric of reality itself became metastable, like water superheated past its boiling point, desperately holding onto a state it could no longer maintain. The transition would not happen everywhere at once. It would begin with a quantum shudder, a tiny bubble of the new, stable reality spontaneously popping into existence within the old, false vacuum. And once that first bubble formed, all hell would break loose. This is the moment the universe began to boil. Within the superheated, metastable state of the old phase, quantum fluctuations provided the necessary spark. At random points in space, tiny bubbles of the new, stable reality would spontaneously nucleate, like the first steam bubbles forming at the bottom of a pot. These were not bubbles of air in water, but spheres of a fundamentally different vacuum state, where the cosmic fields had already settled into their lower energy valleys. Each bubble represented a pocket of true stability in a sea of precarious, false vacuum. And once one of these bubbles appeared, it did not linger. The pressure difference between the stable interior and the unstable exterior was unimaginably vast. Driven by this colossal energy difference, the bubble walls expanded outward at a significant fraction of the speed of light, often approaching it. Imagine trillions upon trillions of these spheres erupting across the cosmos, each one a growing domain of the new universe, relentlessly consuming the old. The interior of a bubble was calm, settled into its new cosmic rulebook, but the wall itself, the boundary between the old and new phases, was a site of unimaginable violence. This thin, propagating membrane contained the entire latent energy of the transition, a concentrated sheet of energy density moving through space. The true chaos began when these expanding bubbles met. As they grew, they inevitably collided. When two bubble walls smashed together, the energy contained within them did not simply vanish. It was released in a cataclysmic shockwave, a torrent of radiation and fundamental particles. Space itself would have rippled from the impacts, and it is here we find a potential scar of a different kind, not a frozen topological defect, but a permanent vibration etched into the fabric of spacetime. The collisions and the subsequent complex sloshing of energy would have shaken the universe to its core, generating a cacophony of gravitational waves. These ripples in spacetime, born from the violence of bubble collisions, would still be washing over us today, a faint hum telling the story of the universe's most explosive rebirth. That hum would be a direct message from the moment of transition. These primordial gravitational waves are fundamentally different from the light we usually use to see the universe. Light from the first stars or the cosmic microwave background interacts with matter. It scatters, it gets absorbed, it is blocked. For the first several 100,000 years of the universe, it was completely trapped in a thick fog of plasma. This means our view of the cosmos before that time is completely dark, but gravitational waves are not light. They are ripples in the geometry of spacetime itself. They pass through matter, energy, and even that primordial fog almost completely unimpeded. A gravitational wave generated in the first fraction of a second after the Big Bang would travel across the entire age of the universe unchanged and could in principle be detected here and now. It carries a clean, unaltered snapshot of the violent event that created it. The signal we would be looking for is not a single chirp like the ones detected from merging black holes. It would be a stochastic background, a cosmic sea of overlapping waves from countless bubble collisions or a vibrating network of cosmic strings, all combining into a persistent, low-frequency hum permeating all of space. To hear this ancient echo, we need exquisitely sensitive detectors that operate on a galactic scale. One method uses nature's own precision clocks, millisecond pulsars. These are the rapidly spinning cores of dead stars, beaming out radio pulses with the regularity of an atomic clock. By monitoring an array of these pulsars across our galaxy for years, astronomers watch for tiny, correlated shifts in their pulse arrival times. A passing gravitational wave background would stretch and squeeze the spacetime between us and the pulsars, making the pulses arrive slightly early or late in a predictable pattern across the sky. Another approach is to build a gravitational wave observatory in the quiet of space. The Laser Interferometer Space Antenna, or LISA, is a future mission that will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart. By firing lasers between them and measuring the microscopic changes in distance, LISA will be tuned to listen for the low-frequency rumble of these primordial events, a frequency range where the echoes of cosmic bubble collisions are predicted to ring loudest. The hunt is already on, and the first hints of a background hum have possibly been heard. The challenge is proving it comes from the universe's infancy and not from a chorus of closer, astrophysical sources like orbiting supermassive black holes. Finding the right note in that hum could be our first clear recording of creation's most violent instance. While gravitational waves offer a direct recording, there is another, older snapshot we can examine. The cosmic microwave background is that first light, released when the universe became transparent, and it serves as a photographic plate of the cosmos at only 380,000 years old. Any scar, any defect, any violent ripple that existed at that time would have left its mark on this light, subtly warping its journey to us. The patterns we see in the CMB are not random noise. They are a fossilized imprint of the conditions of the infant universe. To find evidence of phase transitions, we must look for specific telltale signatures etched into this ancient glow. The most straightforward might come from cosmic strings. Picture a universe crisscrossed by these ultra-dense filaments. As the primordial light from the CMB passes by a string, the immense gravity of the defect would act like a lens, bending the path of the light. This would create a very specific kind of distortion, a sharp, step-like discontinuity in the temperature of the CMB along a line in the sky. It would be as if someone took a nearly smooth photograph and made a single, perfectly straight cut, shifting one side slightly against the other. Astronomers have searched for these telltale edges in high-resolution maps of the CMB, but so far, no definitive string has been found, placing strict limits on how dense such a network could be. A more subtle and perhaps more promising signature lies not in the temperature of the CMB, but in its polarization. Light from the early universe is polarized, meaning its electric field vibrates in a preferred direction, like light reflecting off water. This polarization carries a deeper story. It can be split into two types. The first, called E-mode polarization, is a curling pattern that arises naturally from the gentle swirls of density in the primordial plasma, like the pattern you might see in scattered dust. The second type, B-mode polarization, is a twisting, curl-like pattern. This is the crucial one. While certain fluid motions can create a faint version, a truly primordial B-mode signal is the smoking gun for gravitational waves rippling through the early universe. And this is where phase transitions connect directly. The violent collisions of bubbles in a first-order transition, or the relentless shaking of a cosmic string network, would have flooded the cosmos with gravitational waves just before the CMB was released. Those waves would have squeezed and stretched the fabric of space, imparting a distinct, twisting signature onto the polarization of the CMB light as it began its journey. Finding this specific B-mode pattern is one of the holy grails of modern cosmology. It would not just confirm the existence of primordial gravitational waves, its precise characteristics, its strength, and how it varies across different angular scales in the sky could tell us what created them. The signal from cosmic strings would look different from the signal from colliding bubbles, which would in turn differ from the signal predicted by cosmic inflation. It is a cosmic fingerprint, and researchers are building incredibly sensitive telescopes at the South Pole and planning new space missions with the explicit goal of reading it. The oldest light in the universe may still hold the clearest picture of its most violent childhood moments. But among all these grand, speculative events, there is one phase transition we know for certain happened. It is the most recent and the best understood, occurring when the universe was a mere picosecond old and still at a temperature of about a quadrillion degrees. This is the Electroweak phase transition. Before this moment, two of the four fundamental forces we know today, the electromagnetic force, which governs light and chemistry, and the weak nuclear force, responsible for certain kinds of radioactive decay, were unified into a single, symmetric electroweak force. Particles like the W and Z bosons, which today are quite massive, moved through the hot plasma as if they were weightless, much like photons still do. Then, as the cosmos expanded and cooled past that critical quadrillion-degree threshold, everything changed. The unified electroweak force broke apart into the two distinct forces we observe. But more importantly, this was the moment the Higgs field, which permeates all of space, settled into its current non-zero value. Think of it as the field finally choosing its stable valley in that energy landscape. This process, called electroweak symmetry breaking, is what gave mass to the W and Z bosons, and to all the fundamental matter particles like electrons and quarks. In essence, this transition is why particles have mass at all. The question for cosmologists is not if it happened, but how. Did the Higgs field roll smoothly and gently into its new state, like a marble descending a shallow, rounded bowl? This is what physicists call a smooth crossover, and it is the prediction of the simplest version of our standard model of particle physics. A smooth transition would have been quiet, leaving no dramatic scars for us to find. Or did the transition occur violently as a first-order phase transition? In this scenario, the energy landscape would have had a barrier, like a small hump in the middle of the bowl. The universe would have remained stuck in the old, symmetric phase even as it cooled, becoming metastable supercooled. Then, bubbles of the new phase, where the Higgs field had found its true value, would have suddenly nucleated and expanded at nearly light speed, violently converting the entire cosmos. This kind of dramatic event could have generated powerful gravitational waves and potentially created other defects. The nature of this transition is not just academic. It has profound implications for one of the universe's great mysteries, why we exist at all. The observable universe is made almost entirely of matter, with very little antimatter. This overwhelming imbalance, called baryogenesis, requires specific conditions to have occurred in the early universe. A violent, first-order electroweak phase transition could have provided the perfect environment. The expanding bubble walls could have acted as cosmic filters, separating particles from antiparticles and leaving behind the matter-dominated cosmos we see today. So, determining the character of this transition is a major goal. It pushes at the boundaries of known physics. If it was first order, our current standard model is incomplete. We would need new particles or forces to shape that energy landscape into the right form. This makes the search for the scars of this event, a specific signature in gravitational waves or subtle imprints elsewhere, a direct hunt for physics beyond what our largest particle colliders have yet revealed. The electroweak transition is our closest, most tangible link between the cosmic drama of the infant universe and the fundamental laws that govern our reality today. Just moments after the electroweak transition, the universe continued its relentless cooling and expansion, setting the stage for another profound transformation. This one would forge the very building blocks of the world we know. We are entering the era of the quantum chromodynamic, or QCD, phase transition. By this point, the universe was a seething ocean of fundamental particles. Quarks, the tiny, indivisible constituents of matter, and gluons, the particles that carry the strong nuclear force, raced through a plasma so hot and dense that they could not bind together. They moved freely like ingredients in a cosmic soup, but as the temperature plummeted below 2 trillion degrees Kelvin, roughly a microsecond after the Big Bang, the nature of this soup changed forever. The strong force, which is incredibly powerful but only acts over minuscule distances, finally gained the upper hand. In the hot plasma, quarks and gluons had too much energy to stick together. But as the universe cooled, that energy bled away. Suddenly, the strong force could bind quarks into permanent partnerships. Trios of quarks snapped together, forming the first protons and neutrons. This was the moment the quark-gluon plasma underwent a phase transition, condensing into the familiar particles that would later become atomic nuclei. Unlike the electroweak transition, most theories suggest this QCD transition was likely not a violent first-order event, but rather a smooth crossover or a very gentle shift. Think of it not as water boiling, but as a thick syrup gradually thickening as it cools. Because it was likely so smooth, it probably did not create the dramatic, universe-spanning defects like cosmic strings or domain walls. The transition was more of a quiet consolidation, a settling into a new normal. Yet, even a smooth transition in the fabric of reality can leave subtle marks. One intriguing possibility is the formation of strange quark matter. Under the extreme pressures of this transition, some theorists propose that pockets of a bizarre, stable substance could have formed, a dense lump composed of roughly equal numbers of up, down, and strange quarks. These hypothetical objects, called strangelets or quark nuggets, could have survived to the present day as dark, dense relics drifting through the galaxy. If they exist, they would be a direct, tangible scar of that microsecond moment, a frozen droplet of the primordial quark-gluon plasma. The transition may have left another, more ghostly imprint on the cosmos. The way protons and neutrons clumped together in those first moments could have sown the seeds for all future structure. Tiny, random density fluctuations from this process might have been amplified by gravity over billions of years, subtly influencing where galaxies and galaxy clusters eventually formed. So while we may not find vast walls or cosmic strings from this event, its legacy is written into the large-scale architecture of the universe itself. Every atom in our bodies contains protons forged in that brief, critical window. The QCD transition did not tear the cosmos with dramatic scars. Instead, it stitched together the fundamental fabric of matter, setting the stage for everything that was to come. But to find the most dramatic and enduring scars, we must look back even further to a time of almost unimaginable energy. Before the strong force and the electroweak force went their separate ways, many physicists believed they were one. This is the realm of grand unified theories, and the phase transition that shattered that unity would have been the most cataclysmic event in the early cosmos. Picture the universe in its first fleeting instance, a time so early we measure it in negative powers of 10. At these energies, a quadrillion times hotter than the core of our sun, a single, sublime force governed all interactions. There was no distinction between the force that binds quarks and the force behind radioactive decay. In this state of perfect symmetry, the cosmos was elegantly simple. Then, as expansion cooled the universe to a mere 10 to the 29 degrees, this supreme symmetry broke. The single grand unified force fractured, with the strong nuclear force peeling away from what would become the electroweak force. This was not a gentle shift. The energy scale of this event is so vast it defies earthly comparison. Our most powerful particle colliders operate at energies a trillion times smaller. We are discussing physics at the doorstep of the Planck scale, the fundamental limit where our understanding of space and time itself breaks down. Because of this incredible energy, any defects formed here would be monumentally stable and heavy. This grand unification transition is the prime suspect for creating the most sought-after relics. Magnetic monopoles, those isolated magnetic charges, would have been produced in staggering numbers, like frost crystallizing across a window pane. Cosmic strings, if they formed, would be unimaginably dense, perhaps with the mass of an entire planet compressed into every mile of their length. These would not be subtle features. They would be permanent, glaring scars etched into the cosmos during its first moments of differentiation. Finding one, even a single magnetic monopole or the signature of a cosmic string network, would be more than just a discovery. It would be a direct message from that epoch of ultimate unity. We would be holding a piece of evidence from the moment the fundamental rules of our reality were set, a fossil from the universe's first and most decisive act of self-definition. The hunt for these objects is in essence an attempt to probe energies we can never hope to recreate, using the cosmos itself as our laboratory. Yet this vision of a cosmos littered with grand unification relics presents a profound puzzle. If these phase transitions happened so early and produced such heavy, stable defects, why isn't our universe absolutely filled with them? We should be swimming in magnetic monopoles, and cosmic strings should crisscross the sky in a dense, observable web. Their apparent scarcity is one of cosmology's great mysteries, and its most compelling solution introduces another monumental idea: cosmic inflation. Think of inflation as the universe's great reset button, or perhaps its ultimate eraser. This theory proposes that a fraction of a second after the beginning, the cosmos underwent a period of exponentially faster than light expansion. In an unimaginably short time, a subatomic speck of space was blown up to a size larger than our entire observable universe today. This concept solves several major problems, but for our scars, it has a dramatic consequence. Any network of cosmic strings, any population of monopoles created before inflation began would have been stretched apart. The defects would be pushed so far beyond our cosmic horizon that they become effectively invisible, their density diluted to nearly zero. Inflation smooths over the early universe's wrinkles, ironing out any primordial imperfections. So does this mean our search for these scars is futile? Not at all. In fact, inflation might be the very reason we have a chance to find them. The key is timing. Inflation was not the beginning. It was an event, and like other events, it had a start and a finish. Many models suggest that inflation itself was triggered by a phase transition. a quantum field rolling down its energy hill into a new state that provided the repulsive gravity to drive the rapid expansion. More importantly, when inflation ended, that field did not simply stop. It oscillated wildly at the bottom of its valley, a turbulent period cosmologists call preheating. In this chaotic, energetic finale, as the immense energy of the inflattened field decayed into the hot soup of particles for the Big Bang proper, conditions could have been perfect for new phase transitions to occur. Symmetries could have broken again right at the dawn of the universe we recognize. Any defects formed after inflation ended would not have been erased. They would have been imprinted onto a freshly smoothed, enormous canvas, and then carried along by normal expansion to the present day. So the cosmic strings or monopoles we hope to detect would not be fossils from before time as we know it. They would be birthmarks formed in the fiery moments of our universe's true awakening, after the great smoothing but before the first structures emerged. This elegant idea resolves the conflict. Inflation cleans the slate, wiping away any pre-existing clutter, and then the subsequent phase transitions of grand unification or electroweak symmetry, breaking right their signatures onto that clean slate. Our observable universe could still bear those signatures, faint but persistent, waiting in the deep fields of the cosmos or the subtle ripples of ancient light for us to finally read them. This leads us to a monumental, ongoing treasure hunt across the cosmos. Astronomers are not just waiting for a cosmic string to drift into view. They are actively sifting through the universe's deepest data, looking for the subtle, ghostly signatures these defects would leave behind. One of the most promising methods is gravitational lensing. A cosmic string's immense mass, concentrated into a line thinner than a proton, would warp the fabric of spacetime around it. As light from a distant galaxy travels past a string, this warp can act like a strange, linear lens. Instead of creating the distorted arcs or multiple images typical of a galaxy's gravity, a straight string could split a single background galaxy into two perfect, identical mirror images, separated by a razor-thin gap. Teams are now using incredibly detailed maps of the sky from observatories like the Vera C. Rubin Observatory to search for these telltale double galaxies, scanning millions of objects for this precise, unnatural pairing. Another clue might come from the cosmic microwave background that fossilized light from the infant universe. A cosmic string moving at nearly the speed of light would slice through the primordial plasma. Think of it dragging a space-time wake behind it, a step-like discontinuity in the temperature of the CMB. It would create a very sharp, linear edge in the heat map of the early cosmos, a cold line next to a hot line. Detecting such a feature requires exquisitely sensitive measurements of the CMB's fine details. This is a primary goal of instruments like the South Pole Telescope, observing from one of the clearest, driest places on Earth, and the future Simons Observatory, which will map the CMB with unprecedented resolution and sensitivity. They are not just looking for a fuzzy statistical imprint. They are searching for a specific, sharp scar etched directly into the oldest picture we have. The search also extends to the radio sky. The immense energy densities around our oscillating string loop could catalyze the production of radio waves. Some models suggest that as loops decay, they might beep out brief, powerful bursts of radio emission. Others propose that strings could create paired radio sources, two bright spots aligned along a mysterious, invisible line. By cross-referencing massive radio surveys with optical data, scientists hope to find these strange, aligned systems that have no conventional explanation. Each of these methods, lensing, CMB edges, radio signatures, is like looking for a different type of fingerprint left by the same suspect. The absence of a confirmed detection so far is not a failure. It is a process of elimination, narrowing down the properties these strings could have, if they exist at all. This high-stakes endeavor is more than a technical challenge. It is an attempt to touch a relic from a symmetry breaking event that shaped the fundamental forces, to find a tangible thread left over from the universe's first moments. But what if the scars are not things we can see, but something we can hear? The most direct echo from a violent first-order phase transition would not be a silent string, but a roar. The collision of those universe-spanning bubbles of new vacuum, expanding at nearly light speed, would have shaken the very fabric of reality, generating a cacophony of gravitational waves. These are ripples in spacetime itself, and unlike light, they travel unimpeded from that first furious second, carrying a pristine signal across the ages. To detect them, we have built a listening device of staggering scale, using the galaxy itself as an instrument. This is the work of pulsar timing arrays. Scattered across our galaxy are the corpses of massive stars, spinning neutron stars that beam out pulses of radio waves with the metronomic precision of the finest atomic clocks. These are millisecond pulsars, and astronomers have been meticulously recording their ticks for decades. A passing gravitational wave background, a permanent hum filling the cosmos, subtly stretches and squeezes the space between us and these pulsars. Imagine the fabric of the galaxy as a still pond, and these gravitational waves as a gentle, persistent ripple moving across it. As the ripple passes, it changes the distance the radio pulses have to travel to reach Earth, causing their incredibly regular ticks to arrive just a fraction of a second early or late. The key is correlation. A single pulsar's timing drift could be due to anything, but if we monitor an entire array of pulsars scattered across the sky, a gravitational wave background would create a specific, predicted pattern in how their ticks fall in and out of sync with each other. It is like listening to a chorus of perfectly tuned clocks and hearing a faint, synchronized waver in their rhythm. In recent years, collaborations like NANOGrav in North America, along with teams in Europe, India, and Australia, have reported a tantalizing signal. They have found evidence of this correlated timing drift, a low-frequency hum permeating the galaxy. The discovery of this gravitational wave background is monumental, but its source remains the great mystery. Is it the sound of innumerable supermassive black hole binaries merging throughout cosmic history, a predicted astrophysical chorus, or could it be something far more primordial? The frequency and characteristics of the hum could also match the predictions for a network of vibrating cosmic strings, snapping and oscillating as they lose energy. Or it could be the thunderous echo of countless bubble collisions from a first-order phase transition in the universe's infancy. The international effort now is to tease apart this signal, to find its distinctive fingerprint. As more data is collected over the coming years, the hum's precise pitch and volume will become clearer. Each possible source, black holes, strings, or bubbles, sings a slightly different song in the gravitational wave spectrum. Identifying which song we are hearing will determine if we have finally listened to the birth pangs of a fundamental force, a scar written not in light, but in the bending of space-time itself. While we listen for the hum, we are also learning to see in a new kind of light. The oldest picture we have, the cosmic microwave background, holds more secrets than just its temperature map. To find the scars of the universe's birth, we must look at how that ancient light is polarized, the direction its waves vibrate. This is the next frontier, and within it lies a specific, sought-after signature known as B-mode polarization. Think of it as a subtle, curling pattern in the light, a swirl that can only be imprinted by something that twists spacetime itself. Primordial gravitational waves are the perfect sculptor for such a pattern. As they washed through the hot plasma of the infant cosmos, they would have left this distinctive curl frozen into the light, a permanent record of their passage. Finding this B-mode signal is often called the Holy Grail of cosmology, but the story is more nuanced than a single discovery. There are two primary sources for this signal, and they tell different stories on different scales. The first and most famous source is cosmic inflation. If inflation occurred, the quantum fluctuations stretched to cosmic size would have generated gravitational waves of incredible power. These would imprint a B-mode pattern primarily on very large angular scales, corresponding to the vast, smooth stretches of the early universe. This is the direct fingerprint of inflation itself. However, the gravitational waves from a later, violent first-order phase transition, or the ongoing agitation from a network of cosmic strings, would create a similar curling pattern but on smaller angular scales. It is the difference between finding the signature of the universe's initial explosive growth and finding the scar from a specific, shattering event that happened shortly after. Disentangling these signals is the monumental task of a new generation of experiments. At the South Pole, where the air is dry and stable, instruments like the BICEP and Keck array stare at a pristine patch of sky, their sensitive detectors chilled to a fraction of a degree above absolute zero, searching for these faint swirls in the CMB polarization. Their work is a delicate process of elimination, as galactic dust can create a similar polarized signal that must be meticulously subtracted. The future, however, lies in going to space. Missions like the upcoming LiteBIRD satellite, led by Japan, are designed to scan the entire sky from beyond Earth's atmosphere, measuring the polarization with unprecedented sensitivity across a wide range of frequencies. This multi-frequency approach is key, as it allows scientists to map and remove the foreground contamination from our own galaxy with far greater confidence. What they hope to find in the clean data beneath is a pattern. Is it the large-scale swirl of inflation, the smaller-scale imprint of cosmic strings, or the specific signature of bubbles colliding as a fundamental force was born? Or perhaps there will be a complex combination, a layered history written in polarized light. Each possible detection tells a radically different story about the universe's first moments, turning a blurry snapshot of infant cosmos into a detailed forensic report. This elegant dance between theory and observation reveals a profound truth about our quest. The hunt for these cosmic scars is not a simple treasure map leading to a single X, but a complex dialogue between what we can imagine and what we can actually see. The greatest challenge we face is that the specific predictions for these phase transitions, their violence, their timing, the types of defects they might have spawned depend entirely on physics that lies beyond our current understanding. Our trusted standard model of particle physics, while incredibly successful, is incomplete. It does not tell us what happened at those staggering energies of the universe's first moments. So cosmologists and particle theorists work hand in hand, using the cosmos itself as their laboratory. Think of it this way: we have proposed extensions to the standard model, ideas like supersymmetry or theories involving extra dimensions. These are elegant mathematical frameworks that solve certain puzzles, but they come with a vast landscape of possible parameters, like a machine with a million dials and switches we don't know how to set. This is where the search for primordial scars becomes a powerful tool. A confirmed detection of, say, a specific gravitational wave background at a certain frequency, or a network of cosmic strings with a particular density, would be like finding a fingerprint at a crime scene. That fingerprint would immediately tell us which of those million dials on our theoretical machine are set correctly. It would rule out entire families of theories and point decisively toward the true physics of the ultra-high-energy world. In this way, the early universe acts as the most powerful particle collider imaginable, achieving energies a quadrillion times greater than anything we could ever build on Earth. By carefully observing its ancient aftermath, the scars, the ripples, the patterns in the light, we are indirectly conducting experiments on fundamental laws that shaped reality itself. We are not just looking for relics, we are using them to run a diagnostic on the very fabric of space and time. But this elegant detective work comes with a crucial caveat. Every potential clue we find in the cosmos has multiple possible origins. before we can declare we have found a scar from the universe's birth, we must rule out every other, more ordinary explanation. This is the painstaking process of forensic elimination that defines modern cosmology. Take the hum of gravitational waves detected by pulsar timing arrays. That signal could be the long-sought echo of colliding bubbles from a first-order phase transition, or the thrumming of a network of cosmic strings, but it could also, just as plausibly, be the collective rumble from countless pairs of supermassive black holes, orbiting each other in the hearts of distant galaxies, slowly spiraling inward over billions of years. Both sources produce a similar, steady background hum. Telling them apart requires looking for subtle fingerprints in the signal's characteristics, like its exact frequency spectrum and how uniform it is across the sky. It is like trying to identify a singer by listening to a choir. You must learn to pick out one unique voice from a chorus of many. The same rigorous scrutiny applies to the cosmic microwave background. A strange pattern of polarization, a curious cold spot, or a statistical anomaly might make our hearts race, suggesting the imprint of a domain wall or a cosmic string. But first, we must ask, could this be dust? Microscopic grains right here in our own Milky Way galaxy can emit polarized light that mimics a primordial signal. Or could it be an artifact of the instrument itself, a tiny glitch amplified by our immense data processing? Teams of scientists spend years meticulously modeling and subtracting these foregrounds, mapping the galactic dust in exquisite detail, and cross-checking between multiple independent telescopes. The goal is to peel away the local, modern universe to reveal the pristine, ancient one beneath. This process of elimination is not a setback. It is what makes a potential discovery so powerful. The stakes are incredibly high. To claim we have seen a direct relic from a phase transition in the early universe would be a monumental, Nobel-worthy breakthrough. That very gravity means the standard of proof is equally monumental. It requires a signal so clear, so distinct, and seen through so many different observational lenses that all other explanations simply fall away. This relentless cross-examination is what turns a tantalizing hint into a revolution in our understanding. It means that when a signal finally survives this gauntlet of checks, we can have true confidence that we are hearing, at last, the faint whisper of the cosmos being forged. So the ultimate discovery would not arrive as a single, blaring headline. It would emerge instead as a quiet, undeniable consistency across the entire cosmic crime scene. Imagine a detective finding a unique fiber at one location, a partial fingerprint at another, and a witness account that perfectly matches both, all telling the same story. For cosmologists, the conclusive evidence for an ancient phase transition will be a similar convergence of clues from wildly different parts of the observational spectrum. It might begin with a specific, twisted pattern in the polarization of the cosmic microwave background, the signature curl known as B modes at a particular angular scale. That clue alone would be compelling, but on its own, it could still be galactic dust. Then, a separate team, listening to the rhythmic pulses from dead stars across the galaxy, confirms a background hum of gravitational waves. And crucially, the frequency and character of that hum mathematically aligns with what would be expected from the bubble collisions that created the specific B-mode pattern in the CMB. The two faint signals, one in the oldest light and one in the ripples of spacetime, would be singing the same song from the universe's first moments. But the forensic work goes further. This converging story must also explain what we do not see. A successful theory must account for the profound absence of certain scars, like the overwhelming gravitational shadow of domain walls, which would have long since torn the cosmos apart. The complete picture is one of harmony across all channels of evidence. It is the painstaking process of connecting a fingerprint in the light, a whisper in gravity, and the telling silence where other defects should be. Each piece on its own is a mystery, Together, they could form the undeniable portrait of a violent, transformative instant, a moment when the very rules of reality changed in a cosmic flash. This is the standard for a revolution in our understanding. It requires the universe to leave its signature in multiple indelible inks, ensuring that when we finally read the story, there can be no other author. The cosmos we inhabit is fundamentally a relic of those ancient instabilities. The vast cosmic web of galaxies, the very atoms in our bodies, the dominance of matter over antimatter, all of it may trace its lineage back to those violent fraction of a second shifts where space itself changed its rules. This is the profound implication of the search. We are not just looking for curiosities, we are attempting to read the opening paragraphs of our own origin story, written in the language of defects and gravitational echoes. Right now, this search is accelerating into a new era. An international array of next-generation instruments is coming online, each more sensitive than the last. Space-based observatories like LISA will listen for the specific hum of colliding bubbles. Ground-based telescopes in the Atacama Desert and at the South Pole will stare deeper into the polarization of the cosmic microwave background, hunting for the distinctive curl. Pulsar timing arrays will continue their decades-long vigil, refining the signal from the gravitational wave sea. Within the coming years or decades, these tools will deliver an answer. They will either capture the faint but unmistakable signature of a cosmic scar, or they will silence the theories that predict them, forcing us to rewrite our understanding of the universe's first moments. The final chapter of this story is not in a book. It is being written in the silent data streams of these machines, in the subtle patterns of the oldest light and the quiet ripples in space-time. Our history is etched across the sky, waiting for the right moment and the right instrument to reveal its secrets. Stay curious and watch the stars not just for what they are, but for what they were, and for the story their light has carried for over 13 billion years. The next great discovery in physics might not come from a lab on Earth, but from a whisper in the emptiness of space.